Okay, so right now we're going to look at alternative versions of motion maps. Now, when I'm talking about motion maps, and just by default, I'm assuming a position motion map. And a great easy way to draw a position motion map is the way that we saw in the last video, which is just by drawing the positions, velocity vectors, and acceleration vectors all on the exact same diagram. Because really that's where motion maps come from. Imagine you were taking a camera on a tripod, setting it up to record a video or to do like a time-lapse image where you're taking a picture at even intervals of time. You have that frame of reference that you know the distance, the positions, whatever way you want to measure the horizontal location of the object. And then you can see at each frame of the camera where the object is. From that, you can make some deductions about the velocity within that time interval and whether or not the object is accelerating or not. However, other ways that we can do this allow us to figure out other things rather than having to derive it. And that's just by using these number lines, kind of as though they're actually position time graphs, velocity time graphs, or acceleration time graphs. So I'm going to show you those three ways we could do that with this exact same image. So if we're focusing on our position time graph, we have our position time number line. It's the exact same thing that we already saw below, but all on the exact same number line. We're going to place a dot at even intervals of position that correspond with the actual positions the object was at. And those even positions really mean more even intervals of time. So this object starts off at a position of 0 centimeters. And then one interval of time later, I'm showing it's almost at the top of the ramp, maybe a little bit less than 20 centimeters. And then once it's at the top of the ramp, maybe a little beyond, could be like 30 centimeters, and then maybe like 40, and then like 50. So, we have our spacing here. From our first time, where this thing starts, to the end, where this thing ends. We have the exact same number of positions that we had below. We can still draw our vectors on here. This would still correspond with our velocity vector at 0 seconds. This would correspond with our velocity vector at 1 second. Our velocity vector at 2 seconds. This one, which would be the same length, would be our velocity vector at 2 seconds as well. Or we could say v3 if you want to go with the original naming, and we don't know what happens at the end. For this type of motion map, the position motion map, the spacing between those objects can be a great way for us to figure out our velocity, as well as where the object is, what its position is, at those time intervals. However, a new way of looking at this is with our velocity motion map. Rather than placing dots at even intervals of time to show where the object was, we placed dots on this number line to show what the velocity is at those even intervals of time. So for example, we start off with a huge positive velocity. This is the starting velocity because it's in the positive region of our velocity number line, not the negative. And then one interval of time later, it has slowed down. We don't know exactly how much, but I'm just showing it is less velocity. Then after some amount of time after that, it has even less velocity. But then after that, it has the same velocity, and then the same velocity. Notice I have the same number of dots here, but they're not going to be at the exact same positions on this number line, because this blue number line represents velocities, not position. But we can still draw arrows at the start, which is a high positive velocity. The velocity decreases, which is why that arrow is to the left. And then after that, our velocity decreases a little bit more. You know, one thing that I realized is I probably put those dots at the wrong points. See, if it decreased by 1, 2, it would probably decrease by 1, 2 again. So 2 ticks there, because it is decreasing at a constant rate. But once it gets to this point here, where I ended up shifting those dots, it still has some positive velocity because it is greater than 0. But the velocity is no longer changing in this region. Oh, and then once again, this could be that final time where we don't know what's happening here. These arrows do not represent our velocities here. That's what the dots represent. What these arrows are actually representing is our acceleration. That's why I needed to respace these things, is I said because there were two different angles of incline on the diagram, that means there should have been two separate accelerations. For those first two intervals of time, which correspond with the time that the ball was moving up the ramp, those accelerations should have been the same. And then when the ball was on the ramp, that is the second acceleration, which would be the acceleration at the second number, so 0 and then 1, so a1, and that's constant. Okay, and then finally, we have our last representation of motion maps, which is our acceleration motion map. For this one, we still have our same number of dots. We still need to place 5 of them to show those 5 intervals of time, but we're just going to be representing what we are seeing here. So it starts off with this negative acceleration. So I'm going to be placing it in the negative region. So if I start, let's say I start here. Then, one interval time later, it would be here. Same acceleration. The value has not changed, which is why it's at the exact same position on that number line. 1 second of time after that, it is at 0. One interval time after that, it's still at 0. One interval time, it is still at 0, which is where it ends. Now, one thing that will be interesting about this, for the position motion map, we knew that the arrows kind of correspond with these slopes on the position time graph, and those arrows are a way for us to represent the velocity. Same with our velocity motion map. Those arrows correspond with the slopes of the velocity time graph, which represents acceleration. On our acceleration time graph, we don't have a changing slope, except for that instantaneous change from negative to 0 acceleration. We still have that on our acceleration motion map. But at this point, we do not know what that is called. So the arrow does show that the acceleration does go from some negative value to 0. But at this point, we do not have a way to label that. And when that's the case, it is okay to leave it unlabeled. So let's just summarize what we did before we wrap up. Our position motion maps. Two different ways we can draw them. We can draw them as actual dots with velocity and acceleration vectors directly on the diagram that we're looking at. We can set up a number line which has even increments of position on the number line and place dots at even increments of time to represent the positions at those even increments of time. With that approach, we draw our arrows showing the direction of travel from one interval of time to the next. The length of those arrows represents the speed, and the direction represents the direction of travel. Overall, those arrows are the velocity vectors. On the velocity motion map, we have a number line that represents the velocities. The dots are going to be the velocity at those even intervals of time. Here, the arrows represent acceleration. And then finally, on our acceleration motion maps, the number line represents acceleration. Those dots represent the acceleration at those even intervals of time. And as of right now, we're going to leave the arrows on the acceleration motion map unlabeled because we do not know what they represent.